This tutorial we'll be going over the Hess Law lab, and we'll be going over just briefly, more just the conceptual and the steps you're doing, and I'll try to keep the equation and mentioning that brief, and we'll wait till the post lab to go over that more in detail, like how you do the graphs, how you do the calculations. All right, so let's get started. In part one of this lab, we're determining the heat capacity of the calorimeter. So we're actually calibrating the calorimeter is what we're doing. So we're calibrating the calorimeter, and we're using nested coffee styrofoam coffee cups, and they tend to work really great for minimizing heat loss. And but they do actually absorb some heat during the reaction, and we want to try to factor this amount into our heat to reaction calculations. So here's what we're doing in part one. We have a cup and some of the water in here. We're going to start with room temperature water. Okay, and so this is probably going to be around, let's say, like 21 degrees Celsius. And then to this water, and by the way, that's 50 milliliters. And to this water, we're adding 50 milliliters of 70 degrees Celsius water. Okay, it doesn't have to be exact 70, but around 70. So what's going to happen is you'll have 50 ml will be room temperature, will be like 21 degrees Celsius, and then another 50 milliliters will be 70 degrees Celsius. Okay, and you could do a really long math proof for this, but the temperature that these will come to will be, or what's called thermal equilibrium, will be what's called T average, and this is actually 70 plus 21 divided by 2. Um, just a rough calculation here, so this should be, I think, like 45.5 degrees Celsius. Now, this is the theoretical thermal equilibrium. Okay, this is the theoretical number, thermal equilibrium. Okay, so in theory, when these two different temperature waters mix, they should come to, like, this one's going to heat up, and then this one's going to cool down, and then together the TF should be 45. The reason it won't be exactly 45.5 is because when this process happens, when this one heats up and then when this one cools down, when that happens, some of this heat energy actually escapes into the actual styrofoam cup. And it's really clever, the experiment design on how we actually determine this number is what we're going to end up doing is what you actually do is you're going to graph this result, and then over time you're going to measure the rate of heat loss. So after 20 seconds it'll be like right here. Okay, after another 20 seconds it'll be here. Okay, and then so on. So, and I think it says to do this for 3 minutes in the procedure. So this is going to be your temperature on the y-axis, and this will be time. And so, in theory, this should be 45. It should be okay, but it's going to be a little bit less. So this is in theory. Um, but the reason it's going to be a little bit less. So this is our actual, and this is a number that's going to be called T mix here. Okay, and the reason there's a difference here between these two is because of heat loss to the calorimeter or to the actual styrofoam itself. Okay, and then the way you get this number is actually you graph these points here, and then you extrapolate it through when time is 0. So this will be time equals 0 right here. Okay, and so this will allow us to solve eventually for C calorimeter, and we'll go over the calculations at another time. So that's part one, and let me explain why. well, I'll go into part two, and this should help explain why we even do part one. Okay, so part two of the lab is to actually, so so in part two of the lab is we're measuring three different chemical reactions. So we'll be measuring um, the heats of these different chemical reactions. So, like reaction one, I believe is this one. Okay, and we'll be using also a coffee cup calorimeter. Okay, with the thermometer here, and the heat of the reaction. We're going to do this the same way we've been doing these in the past. So the heat of the reaction is since this is an all aqueous environment here. This is called the heat of solution that we'll be measuring. So um, the heat of the solution. So actually, so these are the part of the reaction. Okay, and then these are going to be. This is going to give off some heat. So this is a plus heat. Okay, and we want to capture this number here, and that's going to be, and I'll use red to color code what we're doing here. So this is going to be the heat of solution equals the mass of the solution times the heat capacity of the solution times delta T of the solution. Okay. Now, why did we do part one? We did part one because some of this heat actually goes into the styrofoam cup. Okay, and this is going to be um, the heat from the calorimeter. Okay, so we're gonna add this number. We're gonna add this number to any. We're gonna factor in any heat loss. So this is Q cal, which will equal C cal times delta T the solution. Now, this number is what we obtained from part one. Okay, and realize this number, this will be very small. So this is going to be, and the reason it's small is because the calorimeter works very, very well. So it's not, it's going to take a lot of heat in order to raise the temperature of the calorimeter. Okay, by 1 degree. So this number you should expect it to be pretty small. Now, as for the other numbers here, the mass of the solution is going to be, since we're using 50 milliliters of this, and we're using 50 milliliters of this, and we're doing 50 milliliters of every reactant for all three reactions. So your mass of for each one of these calculations you do, your mass will be 50.0 plus 50.0 milliliters, and this will be 100 milliliters. And in our lab, um, it says to use 1.03 grams per milliliter as the density. So our mass here for all three problems that we carry out is going to be 103 grams. Okay, it also says to assume that the specific heat is the same as water, so we're going to use 4.184 joules per gram times Celsius. And delta T is what we get from the actual thermometer reading. Okay, so this will be our delta T, the heat of solution here. Okay, and this number here will actually be the same number we plug in here, and then again, this is what we get from part one. Okay, step two, as in any calorimetry problem, is we're gonna change the sign here. So you flip the sign because we want to put this in terms of the system. Okay, and the system here is going to be QRXN. Okay, so QRXN equals negative Q solution plus Q cal. Okay, so you flip the sign, and then in step three is we divide by the amount of moles of the system that were used. Okay, and in this case we used 50 milliliters, and all solutions used in this lab are 2.0 moles per liter, 2.0 molar solutions. So, and all the reactions are actually 1 to 1. Okay, which mole amount do you use is actually a limiting reactant problem. But we don't have to sit here and figure out which one's the limiting reactant because we use the same exact mole amount of both reactants. So you just pick one and then you divide by that mole amount. Okay, so this is 50 milliliters, which is actually um, 50 times 10 to the negative third liters times 2 moles per liter. So this ends up being 0.10 moles of system or of reactant. Okay, so we take our whatever we get from part two, which is basically what we got from part one, and we divide it by 0.10. Okay, and this should give us our delta H for the reaction. And always remember the difference between Q and delta H are the units. Q is going to be joules, and delta H is going to be joules per mole or kilojoules per mole. So that's the difference. Okay, so that's the end of our tutorial.